Magnetization and magnetic intensity is the today's topic. Okay, so we shall discuss magnetization and magnetic intensity. Now all these topics as such, they are correlated with the topics which we have discussed in the chapter number 2. Okay, now we have seen that circulating electron in an atom has magnetic moment. Whenever the electron is moving in the orbit in a circular path, then it produces a very small amount of current, because electron in motion is producing electric current, and this current produces the magnetic moment. Now in a bulk material, if you have a big piece of some element, these moments are added vectorially. Vector addition will be there, that of all these atomic magnetic moment, and they will give a net magnetic moment which is a non-zero quantity. Okay, now we define a magnetization as that of magnetic moment per unit volume. Okay, whatever is the magnetic moment that of a particular given bulk material, the total magnetic moment per unit volume is defined as magnetization. It is a vector quantity and it is having its unit ampere per meter. Okay, see, it is total magnetic moment divided by the volume. Okay, and as you know that magnetic moment M is equal to NIA. Now see, current is having the unit ampere and this area is having the unit meter square, divided by the unit of volume, that is meter cube. So meter square will be cancelled out, 1 meter will remain. So its unit is ampere per meter. Okay. Now consider a very long solenoid of small n turns per unit length. Small n is the number of turns per unit length. Okay, and carrying a current I. Now you have this solenoid, okay, which is a long solenoid. What is long solenoid? The length is larger than the radius, or length is very much larger than the radius of solenoid, then it is considered to be an infinitely long solenoid. It has n turns per unit length and it is having current I, and the magnetic field here inside will be, it is mu 0 Ni. Okay, so its magnitude is B0 is equal to mu 0 Ni. Now we try to understand, this part is not given in our textbook, but it is taken in the further derivation, that this small Ni is taken as H. Okay, so this formula will become B0 is equal to mu 0 H. Start writing whenever you are viewing this video in the notebook, so that you can have a reference of all these equations. Okay, so this is very easy to understand now. This is the magnitude of magnetic field. Okay, and we have taken this small Ni as H. Okay, now in the interior of the solenoid, now if you have the solenoid, say for this is a solenoid, okay, this is your solenoid. Now interior of the solenoid is filled with some material, okay, with non-zero magnetization, means it has some magnetic moment per unit volume. Then the magnetic field inside will be greater than the value B0. Earlier, say, there was no material, there was a vacuum. Now we are filling it with some material, then the magnetization of that material is present. When the magnetization of that material is present, means it has some non-zero magnetization, then this solenoid will have a greater magnetic field than B0. Initial magnetic field was B0, now it has changed, and the net magnetic field B inside the solenoid is given by B is equal to B0 plus Bm. Now this equation you can understand, initially there was magnetic field B0. Now this extra magnetic field is produced because of the presence of that magnetic material placed in the solenoid, which has non-zero magnetization. Okay. Bm is the field contributed by the material. Okay, this additional field, that is Bm, this extra magnetic field Bm, is found to be proportional to the magnetization. If more the magnetization, more the extra magnetic field produced. Okay, and Bm can be written as Bm is proportional to magnetization. We put this constant, so Bm is equal to mu 0 m. Okay, Bm is found to be proportional to magnetization. Okay, and we put a constant here, that is mu 0. Okay, now you substitute this equation. Okay, substitute equation 2 and 4 in equation 3. Okay, now what was our equation number 2? Okay, equation number 2 was B0 is equal to mu 0 h. This was our equation. Okay, this was our equation number 2. B0 is equal to mu 0 h. Now you can substitute the value of this second, okay, and this fourth in equation number 3. So in this equation we are substituting. So instead of B0 we write mu 0 h, and instead of Bm we write mu 0 m. So this equation you will have, and mu 0 can be taken common, so it becomes h plus m. This is our fifth equation. Very easy derivation it is. Now we can understand this, that contribution to the total magnetic field inside the sample is due to two things. One is due to external factors such as current in the solenoid. Try to understand how the magnetic field is produced in the solenoid. In the solenoid, when current is passed in all the turns of solenoid, a magnetic field is produced which is B0. Okay, and this is represented by H, because B0 is equal to mu 0 Ni, and we have taken, instead of Ni we have taken H, so it becomes mu 0 H. So B0 is the magnetic field which is produced due to the external factor, that is the current in the solenoid, and the other one is the specific nature of magnetic material. Now whatever material that you are placing here, some substance, say iron rod you are placing, okay, then it has a particular tendency and it has a specific nature, okay, and because of that the magnetic field is produced, and this specific nature of this material which is placed inside the solenoid is represented by magnetization, that is magnetic moment per unit volume. Different material have different magnetic moment per unit volume. Okay, so the magnetic field inside is due to the current passing through the solenoid, okay, and that is represented by this H, and the other is the substance which you are placing inside the solenoid. Okay, now magnetization can be influenced by external factors. External factor means the current. If you have more current, then the magnetization will be more. Okay, this influence is mathematically expressed as m is equal to chi h. Try to understand the concept. Okay, when you are placing the substance here, their magnetic moments of orbital electric current is in different direction. Now when you pass the electric current through the solenoid, then they will try to come in one particular direction, okay, and they will produce a net magnetic moment in this material in one particular direction, that is in the direction of, or rather magnetic field will be produced by this particular magnetic moment. Okay, magnetic moment is the cause of magnetic field produced by this material which is placed. So this magnetic moment is aligned or made in one particular direction by the current which is passing in the solenoid. So magnetization is influenced by external factor. It means the current which is passing through the solenoid, and this influence can be represented as M is equal to chi H. Now what is H? H is N into I. Now if you change the current, then this magnetization of the material will change, or we can say magnetization is directly proportional to this Ni, that is H. Ni is represented by H. So magnetization is found to be directly proportional to the external factor, that is current in the solenoid. So M proportional to H, the proportionality is removed and a constant is placed. That constant is called the magnetic susceptibility. How susceptible the substance is towards the external magnetic field, how flexible the magnetic moment of the substance is, so that it can align in one particular direction when the external current is passed through the solenoid. Okay, chi is the magnetic susceptibility. It is dimensionless quantity. It is a measure of how magnetic material responds to an external field. Okay, it is small and positive for materials which are called paramagnetic. For paramagnetic, its value is small and positive. Small and negative for diamagnetic, and for diamagnetic substance, M and H are found to be opposite in direction. M and H are opposite for the diamagnetic substance. All these small things you should remember for the MCQs. Okay, now substitute the equation 6 in equation 5. Okay, now sixth equation is nothing but the value which we got, that of M is equal to chi H. This M is equal to chi H is placed in the fifth equation. Okay, so there it was mu 0 H, and it was mu 0 into M. Now instead of M we are writing chi H. Okay, chi H is written, H is taken common from this bracket, so it becomes B is equal to mu 0 1 plus chi into H, so it becomes the seventh equation. Now 1 plus chi is taken as mu r, which is relative permeability, and mu r is mu upon mu 0. Okay, so B is equal to mu 0 mu r into H. Instead of this 1 plus chi, it is written as mu r, so our equation becomes mu 0 mu r into H. Okay, and mu is nothing but mu 0 into mu r. Okay, you can write this mu as a subject of formula, and you can have mu r into mu 0, and mu r is nothing but 1 plus chi. So instead of this mu r, we can write 1 plus chi. So the permeability of the material can be mu 0 into 1 plus chi. Okay, and this mu 0 mu r is nothing but permeability of the substance. So instead of mu 0 into mu r, it is written as mu. So B is equal to mu H. Okay. Now magnetic properties of the material. Okay. Now see, different material are having different magnetic properties, and that is mainly depending upon the different factors like susceptibility, okay, then its magnetization and all. Now see, magnetic material are basically classified in diamagnetic, paramagnetic and ferromagnetic. In terms of susceptibility, chi, a material is diamagnetic if chi is negative. So these are the classification. If chi is negative, it is called the diamagnetic substance. Okay, it is paramagnetic if its chi is positive and small, and ferromagnetic chi is large and positive. Susceptibility is large and positive, then it is a ferromagnetic substance. Now this is the table in which different values of the chi is shown. Diamagnetic, it is in between 0 to -1. Okay, you can see for paramagnetic it is 0 is less than chi, less than some value. Okay, that is a small value for paramagnetic, and chi is very large for the ferromagnetic substance. Okay. Now we shall talk about diamagnetism. Diamagnetic substances have tendency to move from stronger to the weaker part of the external field. It means these diamagnetic substances are repelled by the external magnetic field. Okay. We know that magnet attracts metals like iron bar rather. Okay. Magnet would repel a diamagnetic substance. Okay. So here the diamagnetic substance are repelled, it is T. We know that magnet attract the metals like iron, but magnet would repel the diamagnetic substance. Okay. Here one figure is given in this, a diamagnetic bar is placed in the external field. You can see that this is the external field lines. Okay. These are the external field lines, and they are found to be expelled away by the diamagnetic bar, or they do not pass through the diamagnetic substance, they are going away from the diamagnetic substance. The field lines are repelled or expelled, and the field inside the material is reduced. This reduction is very small, being 1 part of 105. Okay. So it is 105 fifth part of the 1. Okay, very small reduction, but reduction will be there. When this bar is diamagnetic substance, okay, placed in the non-uniform magnetic field, then what will happen? The bar will tend to move from high to low field, from stronger field to the weaker field, the diamagnetic substance will go. The simplest explanation for diamagnetism is given here. Now see, electrons in the atom are orbiting around the nucleus. They possess orbital angular momentum that I have explained earlier. These orbital electrons are equivalent to current carrying loops. The electrons which are moving in the orbit, they are considered to be a current carrying loop, and they possess the orbital magnetic moment. Now diamagnetic substances are the one in which resultant magnetic moment in an atom is 0. So resultant magnetic moment in the diamagnetic atom is 0. When magnetic field is applied, the substance develop a net magnetic moment in the direction opposite to that of field. Now see, if you want to understand it, then if you have, say for example, you have this diamagnetic bar. Now there are current loops. One is having an orbital magnetic moment in this direction, the other one is in this direction. Okay, they all are in random direction. So their net magnetic moment in the bulk material will be equal to 0. Now see, magnetic field is applied. It is always from external north to south. Okay. So magnetic field is from left to right. Now all this magnetic moment will be aligned in the opposite direction to the applied field. Now applied field is from left to right in this direction. All these magnetic moments which are there inside the bulk material, all this alignment will be in this particular direction. All will align in the opposite direction of the magnetic field. Okay, and that is why they experience the repulsion. Now examples of diamagnetic substance you should remember in MCQ, they can be asked: bismuth, copper, lead, silicon, nitrogen and STP, water and sodium chloride. Now when metals cooled at very low temperature, they exhibit superconductivity. Now this you have to remember, or you should understand. Okay, whenever the metal is cooled down, its resistance reduces, and if it is cooled down below a certain critical temperature, then it behaves as a superconductor, or we can say superconductivity is a phenomena which is exhibited by the metal at a temperature below some critical temperature. Okay, now these metals at very low temperature exhibit both perfect conductivity and it is a perfect diamagnetism. So it is a perfect conductor, no resistance as such, very low resistance, negligible resistance. It behaves as perfect diamagnetic substance also. Okay, here what will happen? Field lines will be expelled out. They will not pass through the diamagnetic substance and they will be repelled by the diamagnetic substance. No field line will be passing through the diamagnetic substance, and at that time the value of susceptibility will be -1 and mu r will be equal to 0. This is for superconductor. Okay, MCQ can be asked based on this. Okay, now a superconductor repels a magnet, and by Newton's third law it is repelled by the magnet. So superconductors are repelling the magnet and magnets are repelling the superconductors. Okay, and this phenomena of perfect diamagnetism is useful in the magnetic levitated train. Okay, and this was first invented by the scientist Michener. So this phenomenon is also known as Michener effect. Okay, superconducting magnets are used in variety of situations. For examples, for running magnetically levitated superfast train. Okay, thank you very much.